trouble. So that the general gauge mediation has, in general, the GEDC problem. That's something to think about. Okay. Now, we can also go on to look at the fermion masses, but that's just given by a straightforward generalization of what I had before for U1. It's the same linear combination of the currents, and I probably should have said that it's as one check, you can check that this linear combination of currents has to vanish when supersymmetry is unbroken. Supersymmetries tell us that C tilde 1 is equal to C tilde half is equal to C tilde 0. Okay, so this is the obvious straightforward generalization from before. We just sum over the three different gauge groups, and we have to have this group theory factor there, which should be familiar to everybody. Okay, now we can start to learn lessons from fermion masses. First of all, the first comment I want to make is that these fermion masses involve some supertrace-like quantity with different signs for the different terms, so they're not necessarily or not obviously positive. In all the examples that people commonly study, they turn out to be positive, and so for a while we thought there might be a theorem that's not obvious from this formula. However, then we found in the literature there are actually simple examples where the fermion mass squared come out negative, so that's actually bad. That means that the fermions, like the quarks and the leptons, would be tachyonic, and then color and charge are broken if they condense. So anyway, you can find already in the literature examples where this quantity A is manifestly negative for all values of the coupling in the model you write down. So the simplest example we found was a model where supersymmetry is broken basically by an FI model with some extra U1 prime, which you charge the messengers under in addition to the standard model. So if you just work out the messenger mass matrix and then calculate the fermion mass in this model, which is what these people did, you find that they're negative. Okay, so there's no theorem. The second comment I want to make is that from the form of this integral, you see that the typical momentum in this integral there's only one-dimensional scale that we've introduced here. That's what we call m squared. So that tells us that the typical momentum in this integral, which determines the fermion mass squared, is order n. So that means that you can't calculate the fermion mass squared in some low-energy effective theory where you integrate, which is valid below the scale m, where you've integrated out the hidden sector. So you need the full hidden sector to get the fermion mass squared. Another comment I want to make is that, in general, the fermion mass squared should be finite. So you already see that's guaranteed. So that places constraints at large p on this integral. It's nice to see that the leading order term, which is log p, has to cancel by supersymmetry. But that also tells us things about order 1 over p squared, which aren't obvious from supersymmetry. Finally, and this is the main point for general gauge mediation, we see that there are three independent real parameters here, which means that these are parameters which are in principle independent of the gaugino mass two-point functions that we had before. So we see that the fermion masses are not tied to the gaugino masses, nor are they really tied to the gauge coupling, since for each gauge coupling I can presumably cook up a model with whatever value of AR I want. Okay, it's actually interesting to try to do this, but this is all the structure of the theory seems to tell us. Okay, let me also quickly mention another result, which will appear soon. We noticed that there's actually a way of rewriting these formulas, which is very suggestive. So we found that we could write this complex two-point function d of x as two supersymmetry transformations of this j of x, j of 0, and then we could rewrite, morally speaking, what's the linear combination of two-point functions that appears for the fermion masses as 4 supercharged acting on j of x, j of 0. So as a check, you can see that both of these correlators have to vanish when supersymmetry is broken, and that indeed happens, when supersymmetry is unbroken, which is indeed what happens. And this is suggestive of relations in ordinary gauge mediation, which say that the gaugino masses are like 1 power of the Suzy breaking and are holomorphic, whereas the fermion mass squares are holomorphic times anti-holomorphic and go like gaugino mass squared. So, and perhaps there's connections of this to some recent work by other people on the small Suzy breaking limits of general gauge mediation. And okay, I'll skip this comment. So another thing so one other general fact about general gauge mediation that we were able to extract, aside from the counting of parameters, are a couple of sum rules that the fermion masses have to satisfy. Now these sum rules have been derived they have a long history, so I won't even try to repeat it. And so they're well known to people. However, I think their generality perhaps is not fully appreciated. So the sum rules just follow from simple consideration. As I remind you, in the standard model, there are 5 different types of fermions. Right? So there are 3 different quark fields and 2 different lepton fields. So there are 5 different fermion mass squareds per generation. But we see that the most general parameterization of them is in terms of 3 real parameters. So there must be 2 relations per generation. A quick way to derive these relations is to notice that since this is a quadratic Casimir and the U1 symmetries of the standard model, there are 2 U1 symmetries of the standard model that are anomaly free, then that immediately implies that the relations must take the following form. Okay, so again, these relations have been derived in the context of various gauge mediation models, but here we see that they're fully general. And of course, these relations are meant to be valid at the scale n, at the scale in which we integrate out the hidden sector, and then small corrections, you can show that there are small corrections from a normalization group flow down to the weak scale, and also electroweak symmetry breaking. Okay, so now let me conclude with the summary. We've constructed a framework, which I hope is just a starting point for analyzing general models of gauge mediation, by which we define the arbitrary hidden sectors which break supersymmetry spontaneously and couple to the MSSN via standard model gauge interactions, and only couple to MSSN via these interactions. So we used our framework to understand some of the general predictions of gauge mediation, and we counted the parameter space and came up with the following. So we have 3 complex parameters which basically parameterize the gaugino masses, and 3 real parameters which parameterize the 5 different fermion masses per generation. So our framework is suitable now for analyzing strongly coupled hidden sectors. That's sort of why we work in terms of currents and things. And one step in this direction was recently taken by these people in the context of n equals 2 strongly coupled gauge theory. Okay, another question, which as part of the outlook, which is something we're interested in, is can you build simple models of gauge mediation, weakly coupled models, models with furions, whatever, which cover the entire parameter space of gauge mediation? So which covers this 3 complex plus 3 real dimensional parameter space. And if so, if you can get such a model, then you can ask what is the minimal construction. So these people recently exhibited generalizations of ordinary gauge mediation with more fields that have the right number of parameters, although it's not clear that they can actually cover the entire parameter space, so there's still something to do here. Finally, a few other things I can mention. It's interesting to wonder whether you can bring the technology of ADS-CFT to bear on any of this. This is something which Herman talked about, but I think there's a lot more to be done, and perhaps in more generality, it's possible to discuss these issues. So in other words, currents and their correlators appear naturally in the ADS-CFT correspondence. One thing we'd like to study are strongly coupled hidden sectors, which the ADS-CFT correspondence is good at. So maybe there's something to do there. And then finally, there's this nagging problem of gauge mediation that's bothered phenomenologists in ON, which is called the mu problem. I don't have time to explain this, but in our paper we tried to translate existing approaches to the mu problem into the general gauge mediation formalism, but the formalism had yet to teach us something new about the mu problem. That was one of the problems. Okay, so I hope that it's interesting to think about general model of gauge mediation and the understanding of physics. And hopefully we're trying to get as clear as we can to the LHC. The time is running out. Not much time left to get all of our stories straight. And LHC is coming, I think, and it'll put the same models to test that inspire fear and apprehension and also excitement in those people who have no models. And so I thought it would be appropriate to help us running out because I'm here to maybe lead with
Would everybody like to add to the fear and apprehension with some good questions?
Yes, so that's something we claim in our work that is always small, pretty much no matter which it is. You can see this by studying the various similar functions and their generalizations. The small gauge currents and is one food based one general prediction of gauge mediation. I get more sense for the data.
Yes.
Right, all the claims I tried to make here were meant to be sensitive to the additional freedom that we would have to add. Those ones tend to affect the Higgs parameters, NHL squared and HL squared. And there are the some rules, for instance, for the third generation to be sensitive. Workable problem sensitive, whatever you add, it's all giving you a problem. So, in fact, that's in our paper, just in time. So, one thing we're trying to do is generalize our definition, take it as a starting point, generalize our definition to include to say that not just the gauge coupling going zero, but also there is additional coupling going zero, decoupled from each other. No, I try to say that we try to translate existing approaches to our framework, but our framework is we haven't shed any light necessarily on. We haven't done any new solutions to the giving problem yet using this framework, and that's I think something which is also on promise potentially. No.
Anybody else? Let's start David again. Washington. Yes, please.
How do you estimate the number of people working in field theory? I don't know. I have no idea. The number of population of the community, I have no idea.
Okay, if there are no more questions, let's thank you again. Thank you very much. Okay, I think our next speaker, which did touch experiments, it's very appropriate for him to close the session. So please, David.
Well, it's customary, and I will thank the organizers for arranging such a wonderful meeting. I think we've all enjoyed it enormously. It was very well done, and especially I liked the wonderful review talks we had at the beginning of each day. However, it's also customary to thank them for giving one the honor of speaking, and I'm not going to thank them. It would have been nice to just enjoy the talks and the wonderful summary that we just heard without having to think of visionary remarks. And so I decided to be totally revolutionary and not use any visuals. No PowerPoint, no transparencies, no blackboard. The real reason is I didn't have time to prepare for it. But it's a challenge, and so at the KXP, many of you know we have this Blackboard seminar tradition, and I once heard Doug Lynn, who is an astrophysicist, rise to the challenge of having to explain to a bunch of string theorists, kinetic matter theorists, all sorts, the theory of planets without using transparencies and all the beautiful pictures that astrophysicists usually show. So he gave a talk standing in one spot, just using his hands, with no other visual aids. It was, talking about stability of planet orbits and formation of planets and everything. It was a tour de force. I can't even approach that, but anyway, that's my excuse for not giving you such a beautiful presentation as we just saw from Hiroshi. I guess Eliezer regards me as one of the few of the old or ancient generation that still remembers what it was like to confront theory with experiments. That brought me back to my first memory of CERN, which was almost 40 years ago. This company began with Gabriele talking about 40 years of string theory. 40 years ago, beginning of string theory was when I first came to CERN as a postdoc. Christopher Owen Smith was here, Alvaro was here at the time, Julius West I met, Mary Kay Gallagher. It was a great, CERN was a vibrant center of theory. It was not the center of the experimental world of particle physics. There were many centers.